Welcome back. Mr. Munyon here with activity 31-2. We're going to be focusing on exterior angles of regular polygons. So we need to know what regular polygons are, and we're going to see if we can't come up with a formula for finding the interior and exterior angles of regular polygons. All right. So first we need to know what a regular polygon is. A regular polygon is probably the type that you learned about in preschool, where all of the sides and all of the angles are equal. So the most basic like pentagon shape that you learned looks something like this. It didn't look, like some weird pentagon. In any case, all the sides are equal, all the angles are equal for regular shapes. Equilateral, equal angular, we need to know that a regular polygon has all equal sides and all equal angles. All right, so it says complete the table and determine the angle measure for each interior angle. So instead of finding just the sum of the interior angles like we did in the last lesson, we want to now divide it to see if it was a regular shape and all the angles were equal, how to find one individual angle on a regular polygon. So all we would need to do is take the sum of the interior angles that we came up with earlier, and a triangle has 3 sides and 3 angles, so divide it by 3, and we get 60 degrees. And hopefully we already know that an equilateral triangle, each angle is also 60 degrees. Same thing with a quadrilateral. A regular quadrilateral, also known as a square, has a sum of interior angles of 360, but if it was regular, all the angles would be equal, so we divide that by 4, and we get 90 degrees. On a pentagon, it has 5 sides and 5 angles, so divide by 5, we get 108 for each interior angle on a regular pentagon. So I'm just going to go ahead and copy down the rest of these, just so we have them. And obviously all we're doing from here is dividing by the number of sides. So if we have a formula to come up with the sum of the interior angles, we take that sum and divide by the number of sides. So right here we've already developed a formula that we could use to figure out one individual angle if we know how to find the sum of the interior angles on a polygon. One individual angle on a regular polygon. All right, so now that we have this, let's graph this relationship that we just came up with. So if we have 3 sides, each individual angle was about 60 degrees, so somewhere around here. 4-sided, it was 90 degrees, so somewhere around here. 5-sided was about 108. 6-sided we got 120. 140, 144, and we don't have 11, but 12 would be the last one there, and we did have 150. In any case, we can tell pretty clearly that this is not linear because there's not a constant rate of change. So what conclusion can we draw about this data? It's not linear. Okay, there's not a constant slope. Slope changes. Whoops, that's kind of ugly there. Let's say the function e represents the measure of each interior angle as a function of the number of sides. Write a rule. Okay, so we already did this on the chart that we made. We know that we could just plug in the number of sides as -2. Basically find the sum of the interior angles using this formula and then divide by n. So this equation right here would represent the graph that we came up with as long as you pick a polygon, so a whole number greater than 3. So we didn't talk about the domain on this one, but just like on the last one we came up with, the domain does need to be greater than or equal to 3 and be a whole number because n represents the sides. So as n becomes greater, what appears to be happening to each angle, the angle is increasing, but not by as much each time. So it's a big jump from 60 degrees to 90 degrees, it goes 30, but then from 90 to 108, it only goes 18. So obviously the angles are increasing, but not by a constant rate. And to be clear, the individual interior angles. I'll go ahead and put that in there. The interior angles. Okay. So now let's look at what an exterior angle is. An exterior angle on a polygon is formed between, if you extend one side of a polygon, it's formed between that extended side and the adjacent side. So basically, if you take a side of a polygon, extend it past the vertex to the outside, this angle that's right here, that's less than 180 degrees that we created, is an exterior angle. So this can happen at every single vertex. If I extend this side, there's another one here. If I extend this side, we create a bunch of exterior angles. And however many vertices there are, that's how many exterior angles there will be. So we have 1, 2, 3, 4, 5. This was a pentagon, so 5 sides, 5 angles, 5 exterior angles. It says use geometry software to draw a convex polygon, extend each side, and then let's explore what happens with these. We're going to find the sum of the exterior angles right here. So let's draw it says pentagon. I'm going to go ahead and use the GeoGebra here. All right, so here we have a hexagon. And you can see that I've already extended the sides and already got the measures of these angles on here. None of these are very nice, but you'll also notice over here on the side, I have them listed with different Greek letters over here representing them. And I went ahead and added up. This was a hexagon, so I had 6, 1, 2, 3, 4, 5, 6. I added up all 6 of these angles, and notice what happened here. And that's a nice convenient number considering how ugly these were to begin with. But notice what happens if I were to change one of these. It'll affect 3 of the angles here. So as I move this around, 3 of the angles change. But look over here. These 3 are changing. But what happens to the sum as I move this? The sum is always 360 no matter where I put this other vertex. If I pick a different one and move it around, 3 of them are going to change, and the sum stays at 360 degrees, which is convenient. So is that just for hexagons, or is hexagons always 360? Where exactly did this 360 come from? Well, if I look at this quadrilateral, here I started off with a 4-sided rectangle. All of these are 90-degree angles on the exterior because they're supplementary with the linear pair on the inside. If I take one of these and move it around, same thing. These angle measures are going to change. 3 of them will change right here. But the sum is still 360, which is interesting because this is a completely different shape, but the sum of the exterior angles is 360. We know that interior angles, if I was to measure the interior angles, would be different. The sum of the interior angles on a quadrilateral is 360, and on a hexagon is 720. But the exterior angles, it looks like the sum, no matter what shape it is going to be 360. So going back to our question, a little bit too far there, says make a conjecture about the sum of the exterior angles of a polygon within sides. Sum of exterior angles equals, there's not a formula, it's just 360 degrees. And that's true for any convex polygon. Obviously we could make more. You're welcome to go back to GeoGebra and create your own shapes and find the angles and stuff on there, but this is a very convenient formula because it's not a formula. It's just a rule that says the sum of the exterior angles on any convex polygon is going to be 360. Now, to be clear, in case you don't know what convex means, there's 2 types of polygons that could either be convex or concave. So in case you're not familiar with that, you should already be familiar with it. But convex polygons just have an interior angle that's more than 180 degrees, like this one here. An easier way to think about this is if a vertex caves into the polygon, then it's going to be concave because of this big angle right here that's more than 180 degrees on the inside. So, you know, like this one right here, that is not concave, that is convex. This one right here, that is concave because of that angle right there. That vertex caves inside of it. Okay, so hey, great. New rule here that applies to the exterior angles. The sum is always 360. It says predict the sum of the measure of the interior angle of a pentagon and one of its exterior angles. Okay, so let's then talk about relationship between the prediction, use software measure to confirm. Let's use a regular pentagon here. What do we know about the sum of the interior angles? N minus 2 times 180, 5 minus 2, 80, 3 times 180. If we drew the triangles in there, we get 1, 2, 3. We get 540 degrees. And if we divide that by 5 angles, if this was a regular pentagon and all the angles and all the sides were congruent, that would be 108. And if I drew the exterior angle, it would have to be supplementary with that. It would be 72 degrees. The sum, if I did all of these, 72 times 5. So the sum of those exterior angles on a regular pentagon is 360. The sum of the interior angles on any pentagon is going to be 360. All right. It says use your answer from item 12 and what you know about the sum of the interior angles to further prove our conjecture. Basically, we did just prove it. If I have a regular pentagon right here and I know how to find the interior angles, which I do, if it's a regular pentagon, the sum is 540. Each one of these, if you divide 540 by 5, is 108. And then I could use the linear pair to find the exterior. That also proves that the sum of the exterior angles has to be 360. So now it says, let's check your understanding. I would see if you know how to do these. Pause right here and then restart the video. I'll go over these. All right, now that you've had a chance, let's go ahead and go over these now. What is the sum of the interior angles of a regular 24gon? So interior, I use the interior formula. Okay, so sum in terms of n, we plug in a 24. So 24 minus 2 times 180. Let's go to that calculator. All right, we get 3960 is the sum of the interior angles for that one. All right, the question then asks, what is the measure of each interior angle? And it's a regular 24gon, so I know that each interior angle is going to be congruent to each other. So I just divide it by 24 now, and I'll get my answer. So divided by 24. And I get each angle is 165 degrees. 3960 divided by 24 equals 165 degrees. We get the sum equals 3960, and each angle is 165 degrees. So number 15 says, how does the sum of the measure of the exterior angles of a convex polygon differ if the polygon is regular? So for the exterior angles, remember, doesn't matter what kind of convex polygon it is, whether it's regular or not regular, the sum is always 360. It doesn't matter. There's not even a formula or anything. Doesn't matter if it's regular or not regular. The sum is always 360 degrees. And that's what we were exploring on the GeoGebra there. Number 16 says a convex polygon has exterior angles that measure 70, 105, 28, and 32. What is the measure of the fifth exterior angle? Well, because we're dealing with exterior angles, it doesn't matter how many there are. We know that there's going to be a sum of 360 degrees. So the sum equals 360 degrees. If it's a pentagon, there are 5 angles, so we're only missing one of them. And if we know 1, 2, 3, 4 of them, I can subtract off the ones that I do know and see what I'm left with for the last angle, because that last angle has to add up to the sum of 360. and plug that in our calculator, and we end up getting 125 degrees left for the last angle. So the last angle has to be 125 degrees. All right, number 17. Each exterior angle of a regular polygon measures 24. How many sides does the polygon have? There's a couple of different ways to do this one, but I know that the sum has to equal 360. All right, and that is made up of taking each of the exterior angles and multiplying it by the number of sides. So if this is a regular polygon, all of the exterior angles are going to be the same. So I don't know what the number of sides is, but I know that there are 24 of them times however many there are has to equal 360. Right? All you have to do is divide both sides by 24. And for this one, we end up getting 15. So that means it has to have 15 sides. Okay, and if you wanted to, you could actually check your work by finding the interior angle on a regular 15-gon and then using a linear pair to find the outside. So if you did, n minus 2 times 180, so n minus 2 is 13 times 180, and then divided by 15, you would actually find out the interior angle, and then the supplement should be 24. So let's check that one real quick just to make sure. 13 times 180 divided by 15. We do get 156, and 180 minus 156, the supplement, does equal 24. So great. Turns out that does work to check our work on these. All right, same thing with the lesson practice. I want you guys to take a moment here and see if you can answer 18 through 24. Pause the video, give it some time, see if you can solve these, and then come back and check your work when you're done. All right, now that you've had some time, I'm going to put some answers for all of the A questions on here, and then I'll work the B questions for you. All right, I went ahead and put all of the answers on here, but I will go over the B questions on here. So 18B says find the sum of the measures of the interior angles of each regular polygon. So the sum of the interior is the formula n minus 2 times 180. So if you plug in 18, you do get a 2880. Question 19 says the expression a minus 4 represents the measure of an interior angle of a regular 20-gon. What is the value of a in the expression? So for if you want to find one interior angle of a 20-gon, you need to find the sum and then divide by the 20 congruent angles. So 20 minus 2 times 180 over 20, you'll end up getting 162. So we end up getting that each interior angle is 162 degrees. So if this expression represents that, you add 4 to both sides, and we get A has to be 166. For question number 20, it says find the measure of each interior angle of a regular polygon. You just need to do n minus 2 times 180 divided by, in this case, 18. So 18 minus 2 times 180 will get you the sum of the interior angles. And then if you want to find one individual angle, you divide by the 18 congruent angles, and you'll get 160 on that one. For number 21B, it says find the sum of the measures of exterior angles. 18-gon is definitely going to be, it doesn't matter what it is. If it's a convex polygon, it's going to be 360, which is why we got the same answers for these. On 22, it's kind of the same thing we did for interior, but we're doing it for the exterior. It says the expression n plus 3 represents the measure of an exterior angle of a regular 18-gon. What is the value of n in the expression? Well, 360 divided by 18, because we're looking at the exterior angles, equals 20. So each exterior angle on a 18gon has to be 20. So if this represents each exterior angle, we set those equal. So n plus 3 has to equal 20. Subtract 3 from both sides, n has to equal 17, which is where the 17 came from on that one. For 23, Emilio said that he drew a regular polygon using a protractor and measured one of the interior angles as 100 degrees. Explain using what we know about exterior angles why this cannot be true. So let's go with what we know about exterior angles. If he measured an interior angle of 100 degrees, then the linear pair that was created with that has to be, he drew a 100-degree angle right here. The linear pair, the exterior angle, has to be 80 because it has to be supplementary. And if it's a regular polygon, we know that each of the exterior angles has to be 80, and the sum has to be 360. So if I wanted to find out how many sides it had, I could take 360, divide by 80 to figure out the number of sides. But when you do that, you get 4.5, which could not exist, a polygon with 4.5 sides. So we know that Emilio must have made a mistake somewhere because there's no possible way he could have made it a regular polygon and had an interior angle of 100 degrees. 24 is using the GeoGebra software. If you wanted to go in and do that, you could. It's just about proving the interior angles of a quadrilateral and exterior angles. So we don't need to look at that. Good luck with the activity practice. We do have one more lesson, finding the area of regular polygons now that we know what they are. Let's get to that one.